All right, get ready to dive deep, deep into the world of competitive programming, algorithms, data structures, that kind of thing. Basically, serious problem solving, right?
Exactly. And for this deep dive, our trusty guide is Competitive Programming 3 Foot by Stephen and Felix Halim. They're pretty much legends in the field.
Okay, so how should we approach this deep dive? Should we think of it as like a crash course in competitive programming? Or more of a strategic breakdown, the key concepts?
I'd say it's definitely more strategic. We're going to be going through each chapter, pulling out those valuable bits of knowledge and really understanding why these concepts matter. Think of it as like a cheat sheet to the most important ideas.
I like the sound of that. Let's cheat. So, chapter one, introduction. What's the competitive coding scene all about?
Well, chapter 1 kind of sets the scene. It describes competitive programming as a sport, like a training ground for programmers, right? It's not just about writing code, it's about solving problems efficiently and elegantly.
So, you've got different levels of competitive programmers, right?
Exactly. The book talks about a whole spectrum of them, from casual coders to, those coding ninjas who can solve problems in the blink of an eye.
So, what makes someone a top tier competitive programmer? These all raw talent.
It's interesting, actually. The book talks about this. They say that what distinguishes the very competitive programmer isn't just raw talent, it's more about this unique blend of deep knowledge, strategic thinking, and this like relentless drive to optimize their code. They're constantly seeking ways to be faster, to find those elegant solutions, that just blow everyone else away.
So, it's not just about being a code monkey, it's about having a problem solver's mindset. What other insights did they offer in this introduction?
Well, they really emphasized mastering languages like C++ and Java,
Okay.
but it's not enough to just know the
Yeah.
syntax, right? You need to be fluent, understand the nuances, and be able to use the libraries effectively.
Right, right.
And they specifically highlighted C++, STL, and Java API as essential weapons in a competitive programmer's arsenal.
Makes sense. The better you know your tools, the faster you can work.
Yeah.
What about practical tips for approaching these coding challenges?
Oh, absolutely. They give some really solid advice on tackling these programming problems systematically. First, they really emphasize truly understanding the problem statement, like before even writing any code.
Yeah, that makes sense.
You'd be surprised how many people just jump into coding before they even fully grasp what they're trying to solve.
It's like trying to build a house without reading the blueprints first. It's not going to end well.
Exactly. It's about choosing the right algorithm, debugging effectively, testing rigorously. They really highlight the importance of having a process, a systematic way to approach these challenges.
So it sounds like chapter one is all about setting the foundation, understanding the landscape of competitive programming, equipping yourself with the right tools and mindset. What's next?
Chapter 2 dives into data structures and libraries.
Okay.
And this is where you learn to organize and manage your data effectively to get maximum performance.
Data structures. To be honest, it sounds a little bit dry. This is where we get into like arrays, linked lists, all that.
It does get into the details, but honestly, choosing the right data structure can really make or break your solution. The authors actually do a great job of explaining why.
Okay, so why does it matter so much?
Well, it's about understanding the strengths and weaknesses of each data structure. Like, for example, if you need to access elements quickly based on their index, an array is the way to go. But if you're frequently inserting and deleting elements, a linked list might be a better choice.
So it's about picking the right tool for the job.
Exactly. They cover a whole range of data structures, from the simple arrays to the more complex ones.
What kind of complex ones?
Things like binary search trees, heaps, and graphs. And they explain when and why to use each one.
Okay, got it.
And just like, you wouldn't need dough by hand if you had a stand mixer, you really should leverage those built-in libraries. The C++, STL, and the Java API. They're already there and can save you a ton of time and effort.
It's all about working smarter, not harder. So we've got our tools, our data structures. Now, how do we actually start solving these competitive programming puzzles?
Chapter 3 introduces a fundamental problem-solving paradigm called complete search. And this is where you systematically explore every single possible solution to find the correct one.
Isn't that a bit brute force? Like trying every key on a giant key ring until you find the one that unlocks the door? Wouldn't that take forever for really complex problems?
It can be a bit brute force, and yes, for very complex problems, it might not be practical. But for some types of problems, especially those with a limited search space, complete search can be a surprisingly effective approach.
So how do you make complete search more strategic? What are some of the techniques?
They go into several techniques to make complete search more efficient. Like one is using nested loops. This lets you iterate through all possible combinations of elements.
Right, I see.
Another is generating subsets and permutations, which are basically specific ways to arrange elements within a set.
So it's about being systematic in how you explore the solutions. What other techniques do they talk about?
One of the most powerful techniques is recursive backtracking.
Okay.
This is where you essentially explore different paths. And if a path hits a dead end, you backtrack and try a different route. It's kind of like navigating a maze. You keep trying different paths until you find your way out.
Right, yeah. I could see how that would be really useful, especially for problems where you need to explore lots of different possibilities. Do they have any real-world examples of where recursive backtracking might be used?
Absolutely. Imagine you're building a chess AI.
Okay, yeah.
The AI needs to evaluate different moves, right? Considering all the possible responses from the opponent. So recursive backtracking allows the AI to explore these branching paths, backtracking when it encounters a move that leads to a bad outcome, and choosing the best line of attack.
That's a really good example. It's like the AI is searching through this tree of possibilities, getting rid of the dead branches, and focusing on those paths that lead to victory. What specific problems do they use in the book to illustrate these complete search techniques?
They use a couple of classic examples. One is the 8 queens problem,
Right.
which basically involves placing 8 queens on a chessboard so that no 2 queens can attack each other. It's a great example of how to use recursive backtracking to find a solution that satisfies certain constraints.
So you're just trying every single arrangement until you find one that works. What's the other example?
The other one is UA 441 Lotto.
Okay.
It's about generating all possible combinations of 6 numbers from a set, and it really shows how techniques for generating combinations can be used to solve problems where you need to explore different arrangements of elements.
Okay, so complete search is a powerful tool for tackling those problems where you need to explore all possible solutions. It might not always be the most efficient, but it's a good starting point. So what's next in this world of competitive programming?
Chapter 4 introduces divide and conquer. It's a paradigm that's all about efficiency and elegance. Basically, you break down a large, complex problem into smaller, more manageable subproblems, solve those recursively, and then combine their solutions to conquer the original challenge.
Divide and conquer. Sounds like a military strategy.
It is a bit strategic. Imagine you're trying to sort a giant list of numbers. Instead of comparing each number to every other number, which would take forever, you can use divide and conquer.
Okay, how would that work?
First, you divide the list in half, sort each half independently, and then merge those 2 sorted halves back together. This dividing, conquering, and merging can be applied recursively. So you break down the problem until you're left with tiny lists that are easy to sort.
Like breaking down a complex Lego model into smaller sections, right? You build each section and then put them all together to get that final masterpiece.
Yeah.
So what are some classic divide and conquer algorithms?
The book highlights binary search and merge sort. Binary search is all about efficiently finding a specific value in a sorted array. Instead of checking every element one by one, you repeatedly divide the search space in half. You're basically discarding the irrelevant portion with each step. It's incredibly efficient, especially for large data sets.
So like looking up a word in the dictionary.
Yeah.
You don't start at the beginning. You open it somewhere in the middle, and you just keep narrowing down your search until you find what you're looking for.
Perfect analogy. Merge sort, on the other hand, is all about dividing a list, sorting each half using merge sort recursively, and then merging the sorted halves back together. This ensures the final list is perfectly sorted.
So it's all about breaking things down strategically, conquering the smaller pieces, and then putting them back together into a perfect solution. What are the big benefits of divide and conquer?
They are known for their efficiency. They often have reduced time complexity, meaning they can handle large data sets much faster than brute force approaches, and they can even be parallelized, which means they can take advantage of multi-core processors to really speed things up.
So it's not just elegance, it's practical performance gains as well. I'm liking this divide and conquer approach. What's next?
Chapter 5 is all about greedy algorithms. They're all about making locally optimal choices at each step, hoping that this strategy will lead to a globally optimal solution.
Greedy algorithms. That sounds kind of selfish. What's the idea behind them?
I guess you could say they're a bit selfish. Imagine you're trying to solve the coin change problem, where you need to figure out the minimum number of coins to make a certain amount of change.
Right.
So a greedy algorithm would repeatedly choose the largest coin that doesn't exceed the remaining amount, hoping that this will lead to using the fewest coins overall.
It's like navigating a maze. At each intersection, you just pick the path that seems the best at that moment without really knowing for sure if it will lead you to the exit.
Yeah, there's definitely some risk involved.
For sure.
Sometimes a greedy algorithm works perfectly, and sometimes it leads you astray. The trick is knowing when it's the right approach to use.
So, how do you know when to use a greedy algorithm?
That's where the book comes in handy. It provides a framework for understanding when greedy algorithms are likely to work and when they might not be the best option. They also give specific examples, like the coin change problem and another one called UVa 11450 wedding shopping.
Wedding shopping problem, okay.
Yeah, it's all about allocating your budget across different wedding expenses.
Trying to stay within budget, right?
Exactly, making those locally optimal choices at each step, hoping to maximize your spending power within the overall constraint.
So greedy algorithms are like savvy shoppers, always on the lookout for the best deals, trying to optimize their spending. What's next on our exploration of competitive programming techniques?
Chapter 6 introduces dynamic programming. It's a super powerful way to solve problems by breaking them down into smaller, overlapping subproblems. And the key is, you store those solutions to avoid redoing the same calculations.
Dynamic programming. Okay, I think I get it. It sounds kind of similar to divide and conquer, but with, like, a memory boost.
You're on the right track. Divide and conquer tackles independent subproblems. Dynamic programming deals with overlapping ones. Think of it like having a cheat sheet for your code, right? Once you've solved a subproblem, you just jot down the answer, and if you see it again, you just look it up instead of redoing all the work.
It's about efficiency, not reinventing the wheel. Makes sense, especially when every millisecond counts. So what kind of problems is dynamic programming good at solving?
The book gives some really good examples. A classic one is the Fibonacci sequence.
Oh yeah, I've heard of that one.
Each number is the sum of the two before it, so 0, 1, 1, 2, 3, 5, 8, and so on.
Yeah, I remember. It's like that sequence that pops up everywhere in nature, like those spiral patterns you see in seashells and stuff.
Exactly.
Yeah.
Now, if you try to calculate the Fibonacci sequence the naive way, you end up recalculating the same values over and over. But with dynamic programming, you store those values so you don't have to redo the work. It's a great example of how dynamic programming can really speed things up.
So dynamic programming is like that friend who always remembers the homework answers, right?
Yeah.
Leveraging that past knowledge. What other examples are in the book?
They revisit the coin change problem. They show how dynamic programming can actually be more efficient than the greedy algorithm. And they also tackle the traveling salesperson problem.
The traveling salesperson problem.
Yeah, it's about finding the shortest route that visits all the cities and returns to the starting point.
Sounds complicated. Especially as the number of cities grows, how does dynamic programming help with that?
It's all about breaking it down. You consider all the routes that visit just 2 cities, then 3, and so on, always storing the best distances. This way, you're not repeating calculations. Makes it much more efficient.
It's like building a bridge, brick by brick, carefully placing each one. So we've covered complete search, divide and conquer, greedy algorithms, and now dynamic programming. I'm starting to feel like a competitive programmer. What's next?
Chapter 7 takes a bit of a turn. It's about mathematics.
Oh, math. Okay.
It's a reminder that competitive programming isn't just about coding. It's about understanding the underlying logic, and a lot of that is rooted in mathematics.
I can see that. Math can provide really elegant solutions to complex problems. But what kind of math are we talking about here? Calculus, differential equations.
Don't worry, it's not that intense.
Okay, good.
The book focuses on things that are specifically useful for programming contests. Number theory, modular arithmetic, combinatorics, and probability. It's about understanding how these concepts can help you write efficient code and prove that your solutions are correct.
So it's more about using mathematical thinking as a tool, right? Not just memorizing formulas. What are some examples of how these math concepts come into play?
One cool technique they talk about is binary search the answer.
Right.
It's a way to find a specific value within a range. You keep narrowing down the search space. Super useful when dealing with large data sets.
It's like trying to guess a number, right? Is it higher or lower?
Yeah.
Cutting the possibilities in half with each guess.
Exactly. The book shows you how to apply that to programming problems. They also talk about prime numbers and factorization, which are really helpful for problems involving divisibility, finding factors, and optimizing calculations.
Prime numbers. They're like the building blocks of all numbers, right? Amazing how these fundamental math concepts can have such practical uses in programming. Okay, so we've got some math tools in our competitive programming toolkit now. What's next?
Chapter 8 dives into string processing. It's all about manipulating, analyzing, and searching strings.
Strings, they're everywhere.
Exactly. It's how we work with text and data.
So what kind of string-related challenges do competitive programmers face?
It can be pretty basic, like finding the length of a string or combining strings, but it gets more complex, like searching for patterns, sorting strings alphabetically, or changing them based on rules.
So what are the go-to techniques for dealing with all that?
The book covers a ton of stuff, from basic operations to more advanced algorithms, and they even introduce data structures like suffix arrays.
Suffix arrays. What are those good for?
They're great for things like finding the longest common substring between two strings or checking if a string is a palindrome. Really efficient, especially for super long strings.
So this is useful stuff for anyone working with text, right? Building search engines, analyzing DNA, writing code editors, whatever.
Exactly. Lots of real-world applications.
Okay, what's up next on our deep dive?
Chapter 9 might seem a bit unexpected. It's all about geometry.
Geometry and programming. That's an interesting combo. I guess it makes sense for computer graphics and games.
Yeah.
But how does it apply to competitive programming?
More than you might think. Many programming problems involve spatial reasoning, right?
Yeah.
Calculating distances, figuring out intersections, or manipulating shapes. Imagine designing a navigation system.
Okay, yeah.
You need to calculate distances between points, plot routes, find the shortest path. That's all geometry.
So it's not just abstract shapes and theorems. It's about using geometry to solve real-world problems. What kind of geometric stuff does the book cover?
It starts with the basics: points, lines, polygons, and formulas for distances, areas, and volumes. Then it gets into vectors, dot products, cross products, the tools for working with geometric objects. And then it introduces algorithms for things like checking if lines intersect, finding convex holes, and figuring out if a point is inside a polygon.
Sounds like a whole geometry toolbox for programmers.
Yeah.
Any examples of how these algorithms are actually used in competitions?
One example is robot navigation.
Okay.
You've got a robot in a maze or a room. Geometric algorithms can help you figure out its path, make sure it doesn't crash into anything, and find the most efficient way to get where it needs to go.
It's like those robot vacuums, right? They have
Yeah.
to avoid furniture and stuff.
Exactly. They also talk about placing guards in an art gallery so that every part of the gallery is visible.
Interesting.
It's a classic problem called the art gallery problem. It uses geometric algorithms to figure out the best spots for the guards.
So geometry isn't just some theoretical subject. It's a real-world problem-solving tool. Where do we go from here? What's the final stop on this deep dive?
Chapter 10 takes us to the top, more advanced topics. This is where we get into the techniques that go beyond the basics, really pushing the limits.
Advanced topics sounds exciting and a little bit intimidating at the same time.
Mm.
What kind of concepts are we unlocking in this final chapter?
This chapter is like a treasure chest of advanced stuff. We've got bit mask manipulation, which is a super cool way to represent sets and perform set operations using binary numbers.
Bit mask manipulation. Okay, that sounds like a lot. Can you break it down for me?
Imagine you have a set of items, and you want to track which ones are picked or active. Instead of using an array or a list, you can use a single binary number to represent the whole set.
Okay.
Each bit corresponds to an item. 1 means it's in, 0 means it's out.
So it's a compact code for a lot of information. How does that work in practice?
Let's say you have 8 items. You can represent the set with an 8-bit binary number. So 1011-100001 would mean items 1, 4, 5, and 8 are included.
Makes sense. It's much shorter than storing the actual indices in a list. How do you actually work with these bit masks to do stuff with the sets?
That's where bitwise operators come in handy. AND or XOR, not T. These let you perform operations like union, intersection, and complement. The best part is these operations are really fast because they're supported directly by the hardware.
So it's not just about saving space, it's about speed too. What kind of problems really benefit from this bit mask approach?
They're particularly helpful in dynamic programming problems, where you need to keep track of the system's state. Think about the traveling salesperson problem again. You can use a bit mask to show which cities have been visited already. It's a nice, compact way to keep track.
Bit masks, they're like secret codes for efficiency. What other advanced tools are in this chapter?
We also get deeper into graph algorithms, more sophisticated techniques for analyzing connections and relationships between things.
Graphs, those networks of nodes and edges.
Yeah, exactly. We'll look at algorithms for finding shortest paths, identifying those strongly connected components, and solving problems related to network flow and matching. Super useful for real-world stuff like optimizing transportation and communication systems.
So these graph algorithms are like the brains behind complex networks.
Mhm.
What else is in this chapter?
Finally, we get to some really advanced data structures, segment trees, Fenwick trees, and something called script decomposition.
They sound pretty intense. What makes these data structures so advanced?
These are all about efficiency, specifically for range queries and updates on arrays. Imagine a massive array of numbers. You want to find the sum of a specific section, or maybe the minimum value in a range. That's a range query.
Okay, I can see how that would be useful, but why do we need special data structures for that? Can't we just loop through and calculate the answer?
You could, but it'd be incredibly slow for big arrays. These structures are much faster. They can handle those queries and updates in logarithmic time, which is way better than linear time. Think of them like super organized filing systems. You can find anything you need instantly.
Advanced data structures, they're like the secret weapon of competitive programmers.
They are. Yeah, and what's so cool is that these advanced techniques, they often build on those fundamental concepts we talked about earlier.
Right, it's like leveling up, getting those new skills to tackle tougher challenges. We've gone from basic training to special forces stuff. But we've talked a lot about the technical side, the algorithms, data structures, all that. What about the mental game, the mindset of a competitive programmer?
The book really emphasizes deliberate practice. It's not just about solving a ton of problems. It's about picking the right problems, the ones that push you just outside your comfort zone. It's about understanding why you messed up and learning from it.
So it's quality over quantity, right? Practicing with intention. What other tips did they have for developing that competitive programming mindset?
They talk about breaking problems down into smaller chunks. It's easy to feel overwhelmed, but if you break it down, it becomes way more manageable. And testing your code often, catching errors early, and making sure your solution is solid.
Like building a house, right? You have a plan, you test each step, make sure it's all good. What else about the mental game?
They said to really embrace the challenge, see tough problems as opportunities to grow, and perseverance, not giving up easily, learning to enjoy the process even when it's hard.
It's that growth mindset, believing you can improve through effort. I'm sure even the best get stuck sometimes. What advice did they give for dealing with frustration?
They actually have a whole section on debugging. It's essential for any programmer, but especially under pressure. They say to really read those error messages, test your code thoroughly, use debugging tools to understand what's happening step by step.
Debugging, every programmer's favorite, right? Any
Yeah.
tips for making it less painful?
They suggest print debugging, which is basically adding print statements to your code to track variables and see what's going on. Simple, but it really works.
Like shining a light into the dark corners of your code, finding those hidden bugs. Any other debugging strategies?
Isolating the problem, figuring out exactly where the error is, and sometimes stepping away, taking a break, coming back with fresh eyes. You might notice something you missed before.
Like those optical illusions. Got to look at it from a different angle to see the hidden image. So we've covered a ton of ground. Algorithms, data structures, advanced techniques, and even the competitive programming mindset. What are your final thoughts on Competitive Programming 3? What makes it a great guide?
Honestly, what stood out to me was how well they explain complex stuff. It's clear and engaging. They don't just throw formulas at you. They break it down with examples and analogies that make sense. It's a good book for beginners and experienced programmers.
Yeah, you can tell they really love the subject. They make competitive programming sound fun and rewarding, and it's not just about winning. It's about the problem solving, finding elegant solutions, pushing yourself intellectually. This has been a great deep dive, and I definitely recommend Competitive Programming 3 to anyone who wants to explore this world or just become a better programmer. Thanks for joining us on this deep dive into the world of competitive programming.